and see, that is what is explained here. So Zener diode can be used as shunt regulator. Shunt na Zener diode is considered in parallel. So you have the Zener diode in reverse bias condition. You have the input, you have the output taken from the load. So a Zener diode under reverse bias can be used as used for voltage regulation. So see the simple circuit given. You have the input voltage, you have the series resistance R, and you have the Zener diode in reverse bias condition, and you have the load resistance RL. So the total input current is going to be split into the current flowing through Zener diode plus the current flowing through your load. Okay, so you can see here II is equal to IZ plus IL. So input current is splitting into Zener diode current plus the load current, and voltage across Zener diode is given by VZ, and the load voltage is given by V, and the input voltage is VI. So you have to ensure that the Zener diode is operating in reverse bias, and it provides constant voltage of VZ across the Zener diode. So it is in reverse bias condition. So you know the voltage across the Zener diode remains same even though the parameters are going to change. So that is the beauty of Zener diode. So even though this input voltage is changing, even though the input current is changing, even though the load current is changing, what one thing will be constant? VZ is going to be constant for a Zener diode. So see here, here from this you can from this you can see II is equal to IZ plus IL. So II is the input current, which is splitting into Zener diode current plus the load current. You know from the Kirchhoff's voltage law, you can write VI, so total input voltage equal to the voltage across resistor plus the voltage across Zener diode. So I can write VI is equal to II into R plus VZ. And you know II is equal to IZ plus IL. So I can write VI is equal to IZ plus IL into R plus VZ. So this one formula relates input voltage, Zener voltage, Zener current, and the load resistance. So you can say that this equation is very simple, and this equation is used to design the Zener diode characteristics. So for in this equation, now let us consider this VI is going to increase. Due to some reason, the input voltage is going to increase. So see here, VI is increasing. So in this equation, you see VI is increasing. So naturally, your VZ is constant. So this VZ cannot change. Okay, so see this condition. So when the input voltage is increasing, as the voltage across Zener diode remains constant, so only possibility is this term IL plus IZ has to increase. Okay, so there will be an increase in the current IL plus IZ. As VZ is constant, the voltage across the load will also remain constant, and hence IL will also be constant. Okay, so you know that in reverse bias condition, VZ is constant, and this voltage is applied across RL. So the voltage across RL is constant, so IL is also constant. So only possibility what can change is the IZ. IZ will change. So what happens is when this condition is going to happen, so since IL has to be constant, so IZ will alter itself to ensure that the constant voltage is available across a Zener diode. You're able to understand. So when the input voltage is increasing, since VZ is constant, IL plus IZ only can increase. And among IL and IZ, only IZ can increase because IL is constant. So when the input voltage is increasing due to some unknown reason, your IZ will increase to ensure that the output voltage is constant. So the same happens in the reverse case when the input voltage is going to decrease. When the input voltage is going to decrease, VZ is constant. IL plus IZ also has to decrease. But again, IL is constant. So IZ will decrease itself to ensure that the output voltage does not change because of the change in the input voltages. So that is the beauty. Zener diode will adjust itself. Beauty is VZ is kept constant and IZ will increase or decrease depending on the conditions of your circuit. And this is possible only when you reverse bias your Zener diode. Only when you reverse bias your Zener diode. So it must be ensured that the reverse bias voltage applied to Zener diode should never exceed the peak inverse voltage of the diode. There is a rating called PIV. So PIV is the maximum value of voltage your diode can withstand in reverse bias. So when you are working with Zener diode, whatever voltage you are going to apply should always be less than PIV. So if you are ensuring this condition, then the Zener diode will be very good. And the input voltage should also always be more than VZ. So two things you should always remember. The applied voltage V in, the applied voltage V in should always be greater than VZ, but the applied voltage V in should always be less than the peak inverse voltage of your diode. So this condition is used to ensure that a constant voltage is available across the diode. This condition is used to ensure that diode is not destroyed when it is operating in the breakdown region. So that when you ensure these two conditions are satisfied, then the Zener diode can be used as a pakka voltage regulator circuit component in your circuit. Okay, so that is what I have in Zener diode. So in exams, mostly they might ask the construction of Zener diode and operation, but sometimes they will specifically ask you to explain the voltage regulation property of Zener diode. In that case, you have to explain what is voltage regulation, you have to explain what is line regulation and road regulation, and then you have to explain this circuit, and you have to say how any change in input voltage is going to automatically, the circuit is going to adjust itself for that condition, and the circuit is going to provide a constant output voltage. So that has to be explained very clearly as here, and you have to give the condition relation between V input, VZ and PIV. So these formulas are very much useful for designing the circuit for voltage regulation. Okay.